Good day, welcome. My name is Ian Conlon and I will be discussing the designing of a cylinder for strength. Firstly, to introduce, this is the system that we're working with. The cylinder has a diameter and length that is not known at this stage, but it has a certain thickness. There are different types of forces working onto this cylinder, being pressurized, the weight of the paddles at the bottom, the torque of the motor and the bending moment, and then we'll also be looking at the factor of safety and the thickness of the vessel. The background of a system like this falls with multiple industries, where the food industry would use something like this to mix ingredients. Slurry mixers are used to agitate mixtures, mixture of chemicals and loosening of soil and mixing fertilizer for farms, etc. And I think we can go on quite a bit about that. The reason for failures, this would be for thin wall vessels, where incorrect design strategies are used, inaccurate calculations, wrong material, inadequate testing, inexperienced workers, or poor fabrication methods. All this should be checked with an engineer, or should be done by an engineer, and hopefully a skilled one. In terms of failure of the vessel themselves, there are different types of failing, where the elastic buckling, brittleness failure, corrosion, stress corrosion, materials being too ductile, which means they've got too much strain on them or a high strain on them, instability causing cyclic strain or creep. Next, the problem that we will be dealing with, as mentioned in the introduction, is what range of thickness the vessel is or should be for a different factor of safety, or for a certain factor of safety. Influencing forces on the system would be the pressure, the motor, the paddle and the gear, which causes a bending moment, and all of these have a different influence on the stress in the system. The different considerations that should be taken into consideration is the yield stress, the factor of safety, and the thickness of the vessel. The next part is the analysis. We'll be analyzing all of these 5 parts with the equations and a graphical representation of the system, as well as the calculations. So the calculations and all that for the pressure, the tensile, the torque, the bending moment, and combined. Pressure. The first part that we'll be dealing with is a force due to pressure in the vessel. This force works outwards and then creates two different types of stresses. One being hoop stress and the second one being longitudinal stress. In the calculation you can see that hoop stress is determined to be 40 megapascals and longitudinal stress to be 20 megapascals. The observation can be made that hoop stress is twice or the size of the longitudinal stress, or longitudinal stress is half of the hoop stress. Tensile stress, this stress is due to the force of the paddles due to its weight, or due to the fact that it is mixing the slurry. The weight on this would be 60 kilonewton, and using the formulas provided, which is force over area, we can then determine the tensile stress, which is 15.79 megapascals. Torque. A torque applied by the motor, we've got only the power of the motor and the rotational speed of the motor. Thus we can take the formula power is equal to torque times 2 times pi times the rotational speed in revs per minute divided by 60. And then after that we would need to work out the second moment of inertia, as you can see on the formula, and then the polar moment, which is just twice the second moment of inertia. And if you've got all that information, you can work out this shear stress. As seen on the diagram, you can see the different the shear stress that's applied with the green block and the direction of it, and you can also see the rotation, direction of the motor, and how the force is applied. As follow the calculations, you can see that torque is equal to 31.83 kilonewtons per meter, or kilonewton meter. The moment of inertia, second moment of inertia, is 7.71 times 5 to the negative 10 meter to the fourth. Next, we'll take the second moment of inertia, we will multiply that with 2 to get the polar moment, and with that you will get 1.54 times 10 to the negative 4 meter to the 4. Once we've done all that, we can then determine the shear stress, which is equal to the torque times the radius divided by the polar moment, which then gives us a shear stress of 41.89 megapascal. Next is the bending moment. The bending moment is due to the gear pushing on the vessel from the side to keep it in place. You'll see that the bending, or the vessel has a central axis, and it will bend around that axis to the side, to the opposite side of the force. On the opposite side of the force, you will find the tensile side, and that is also where the maximum stress is applied, due to it being the furthest from the central axis. On the other side, you will find the compressive force, which is negative, which is exactly the same as the max shear, except for it is a negative. The calculations below, you'll see the shear max of the stress max is equal to 60.54 megapascals, where the compressive stress is then equal to negative 60.54 megapascal. Next, the combination of stresses. Different stresses or different forces have a different way of working onto the system. Thus, we can't just plus them or minus them, we need to use certain equations. For the first part, we'll be using the equation sigma x equals sigma L plus sigma T plus sigma B, where sigma L is the longitudinal stress, plus sigma T is the tensile stress, plus sigma B is the bending moment max stress. Once we've got sigma x, we then can plug it into a formula, and which is sigma P1, and sigma P1 is then equal to 112.02 megapascal. Once we've taken that, we can then, or once we've calculated that, we can then use the yield stress, which is 320 megapascals, and divide it by the max, or the principal stress, which is 112.02 megapascals, to get a factor of safety. In this case, the factor of safety will be 2.86. Validation of your calculations is very important to get accurate results. This can help to get less failures in systems. And so at the end of the day, calculations are only as accurate as the decimal points that are used. For example, we'll round it off to the second decimal or the third decimal, where Excel would use the full range of decimals, and that will just yield a more accurate result. Graphically, Excel is a great assistant in visualizing the impact of stresses on the system. In the next few slides, or next two slides, we'll see the graphs that we've drawn up. With this first one is the factor of safety versus the thickness of the vessel. This creates a straight line, and this formula is then used, or the straight line formula is then used with a y value, which is a factor of safety value of 3.5 and 5, to determine the thickness range for the minimum factor of safety to the maximum factor of safety. After we've got that, we can push that into our equations to get the stress, where we've plotted the minimum factor of safety stress and the maximum factor of safety stress with the yellow and the green respectively. We also plotted the stress versus thickness of the vessel to be able to determine an equation for this line, or for this data set, which we can then use that equation to determine what the thickness would be at the maximum or the yield stress. Not that this is very important, but it's always good to see what the minimum thickness of the vessel could be, or should, or will be for it before it fails. So to discuss the factor of safety, the factor of safety is very important, as people can get hurt. If a vessel explodes, large pressures are exerted and massive forces that can kill people or hurt people severely. On the production side, if a machine is broken, you often have to replace it, or you have to, or it is down that you can't use it for a certain time, which you are losing money. And then also the lifespan of the machine. If you design the machine for a longer lifespan, or perhaps a bigger factor of safety, it will last longer, as it can handle more pressure, or it can handle better fatigue. So for this system, for heated pressure vessels, it's known to use a factor of safety of between 3.5 and 5. For this analysis, the analysis of the calculations shows that at failure, which is 320 megapascals, which is the yield stress, the thickness of the vessel is 1.05 millimeters. After that, we take the minimum factor of safety, which yields a thickness of 3.75 millimeters, and it then gives us a stress of 91.57 megapascal. And then after that, we have looked at the factor of safety of 5, which yields a thickness of the vessel of 5.2 millimeters and a stress of 63.97 megapascals. The thickness for the max stress would then be 3.7, and giving us a stress of 91.57 megapascals. In conclusion, the thickness that we would then use for the system to give us a factor of the max stress out of the system would be 3.7 millimeters. However, I would recommend that a 4 millimeter thickness would be used, as it is more standard and it yields a better factor of safety. This might also reduce cost and be readily available, as manufacturing needs to take place to make these vessels or these systems. Thank you very much. Thank you for your time, and hope that was clear. There are my references if you would like to go and check up. Thank you very much.